We're all kind of obsessed with predicting the future, right? Whether it's figuring out where the stock market is headed, what our sales will be next quarter, or even just if we need to bring an umbrella tomorrow. Well, believe it or not, there's a whole science dedicated to this, and it's called time series analysis.
So, think about this for a second. What's the one thing that connects the wild swings of stock prices, the steady rhythm of monthly sales reports, and the constant change of a weather forecast? They seem so different on the surface, but they share one fundamental secret.
It's simple, really. They're all a journey through time. Every single one is just a list of data points collected in order, telling a story over time. One data point follows the next, and hidden inside that sequence, that's where the patterns live.
And that's what we call a time series. But forget the textbook definition for a minute. I love this analogy way more. Think of it as the movie of what actually happened. It's not a guess, it's not a theory, it's the raw, unedited footage of reality. And our job is to watch that movie and figure out the plot.
All right, so that brings us to section 1. Before we even dream of building some fancy prediction model, there's one golden rule we absolutely have to get our heads around. It's like the first rule of forecasting club. You get this right, and everything else just clicks into place.
And here it is, plain and simple. To predict the future, your data needs to have a stable past. You just can't build a reliable forecast on a chaotic foundation. The basic underlying rhythm of your data has to be consistent. And this crucial idea of stability has a name, stationarity.
So what does stationary actually mean? Well, a series is stationary when its core personality doesn't change over time. Picture a river flowing steadily. Yeah, the water level might bounce up and down a little, but it's always hovering around the same average height. It's not slowly trending upwards towards a flood, and it's not drying out. That's a stable, predictable, stationary system.
And you can really see the difference here, can't you? On the left, you've got that stationary series. It wiggles around, sure, but it always comes back to that central average. It's predictable in its behavior. But look at the one on the right. That's non-stationary. It's going somewhere. Its average is clearly drifting upwards. Trying to forecast that series on the right is like trying to hit a target that's constantly moving.
Now here's the real kicker. The data we actually care about most in the real world, things like stock prices, a country's GDP, your company's sales, most of it is non-stationary. It has trends, it grows over time. And that is exactly why getting a handle on this concept is so incredibly important. The classic example of a non-stationary series is something called a random walk. You might have heard it called the drunkard's walk, and honestly, it's the perfect description. Just imagine someone taking a step in a random direction, and then another, and another. Where are they going to be next? Well, basically, wherever they are right now, plus one more random stumble. There's no magnetic pull back to an average. It just wanders off. A lot of people think stock prices behave just like this.
So why are we harping on this so much? Because using unstable, non-stationary data is seriously dangerous. You can end up with what are called spurious regressions, which is a fancy way of saying you find connections that are pure coincidence. It's like that classic funny example. For decades, the number of pirates in the world has gone down, while average global temperatures have gone up. Does that mean a lack of pirates causes global warming? No way. That's a spurious relationship. Your stats tests break down and your forecasts become totally useless.
Okay, so we get it. Stability is a huge deal. But how in the world do you actually check for it? Let's jump into our second section and figure out how we can decode our data's memory to see if it's stable or just wandering around aimlessly.
This really is the million-dollar question, isn't it? How do we tell the difference between a predictable, stable process and that unpredictable drunkard's walk? Well, luckily, we have some diagnostic tools to help us out. Our first tool is called Autocorrelation, or ACF for short. All this does is measure how much today's value is related to yesterday's value, or the value from the day before that, or last week. It's basically asking the data, hey, do you remember what you were doing in the past? For a random walk, that memory of where it's been lingers for a really, really long time. And that's a huge red flag for us. So looking at a chart can give you a pretty good hunch. But if you want the cold, hard proof, a definitive diagnosis for your data, you need a proper statistical test. And that's where something called a unit root test comes in. Now, unit root is just the technical, mathy term for that specific ingredient that makes a series wander off without ever coming back, just like a random walk.
Okay, don't let the name Augmented Dickey-Fuller test scare you. It's actually pretty simple to use. Think of it like this. The test starts out as a total pessimist. Its starting assumption, or null hypothesis, is that your data is non-stationary. It assumes it's unstable. Your job is to prove it wrong. And the way you do that is by looking at one number, the p-value. If that p-value is really small, the standard cutoff is usually less than 0.05, then bam, you've got your evidence. You can confidently reject that initial pessimistic assumption and conclude your data is probably stationary.
All right, deep breath. We've done the hard diagnostic work. We know how to check our data's stability. So now we get to the really fun part, actually building our prediction machine. But before we can build anything complex, we have to start with the most basic building block of all. In time series, that's something called white noise. Think of it like the static on an old TV screen. It's pure, unpredictable randomness. It has zero memory of the past, its average is zero, it's just noise. The whole goal of a good forecasting model is to explain all the predictable patterns in your data, until the only thing left over is this irreducible, random white noise.
So when we build these models, we basically have two main tools in our kit. First up is the autoregressive, or AR piece. This part of the model works on the idea that today's value is probably related to yesterday's value. It has a memory of its own past. Then we have the moving average, or MA piece. This one's different. It works on the idea that today's value is related to the mistakes we made in our forecasts yesterday. So it has a memory of its past errors, and it learns from them to make better predictions.
And this is where the magic really happens, when we start combining these tools. An ARIMA model is a hybrid. It uses both the memory of past values from the AR part and the memory of past mistakes from the MA part. But the real powerhouse model is ARIMA. See that I in the middle? It stands for integrated, and it's a super clever trick that basically takes unstable, non-stationary data and makes it stable before the AR and MA parts do their work. This is why ARIMA models are the true workhorses of so much modern forecasting.
All right, we have covered a ton of ground here. We've gone from the #1 rule of forecasting all the way to the building blocks of these powerful models. So let's bring it all home and talk about the big payoff.
So this is the whole journey in a nutshell. You start with your data. That's your map. Your first and most critical stop is checking for stationarity. If that foundation isn't stable, you just can't trust anything you build on it. Then you put on your detective hat and use your tools, like ACF and unit root tests, to really understand your data's personality. And only then, once you've done that homework, can you build a smart prediction model that actually respects the patterns you found. Because if there's one thing to take away from all this, it's this. To have any hope of predicting the future, you first have to learn how to listen to the story of the past.
And that's where we'll wrap up this explainer. You now have the fundamental rules of the road for forecasting. So I'll just leave you with this final thought to chew on. Now that you know the rules, what journey through time, what pattern in your own world would you want to predict?